In 1969, a young physicist named John Clauser described an experiment he wanted to build to Richard Feynman, then the most admired physicist alive. Feynman threw him out of the office, not because the idea was wrong, because it was pointless. Quantum mechanics was obviously correct, Feynman told him, and testing it amounted to professing a disbelief in it. It needed no further testing. Clauser built it anyway, in a Berkeley basement, out of an oven full of calcium and 2 stacks of glass plates 1.5 meters apart, and ran it for 200 hours. 50 years later, he collected a Nobel Prize. But here is the part that never survives the retelling. Clauser was hoping to prove quantum mechanics wrong, and he lost. And what he and the 2 men who shared his prize actually took away from the world is not what the headlines said. By the end of tonight, you will know exactly what they eliminated and why physics still cannot agree on what is left standing. Before we begin, if following one stubborn question across 90 years is how you like to fall asleep, a quick like or subscribe really helps the channel grow. It means more to me than it costs you. Now, let's ease in. The Nobel Prize in Physics is usually given to people who make the universe easier to understand. That is, more or less, the job description. Someone finds the particle that had been predicted but never seen. Someone works out why a metal loses all resistance to electricity when you cool it far enough. Someone shows that 2 things nobody had connected were the same thing all along, and afterwards the world has 1 fewer mystery in it than it had the day before. The prize is an award for subtraction. It is given for removing confusion from the world. On the 4th of October, 2022, at 11:45 in the morning, the Royal Swedish Academy of Sciences in Stockholm gave the Nobel Prize in Physics to 3 men who had done the opposite. They had not removed a confusion. They had proved that one particular confusion was permanent, and that it was not a confusion at all, but a feature of the world. The 3 names were Alain Aspect, of the Université Paris-Saclay and the École Polytechnique in France; John F. Clauser, an American, listed on the announcement not by a university, but by his own small consulting firm in California; and Anton Zeilinger, of the University of Vienna. Aspect was 75, Zeilinger was 77, Clauser was 79. The prize money was 10 million Swedish kroner, and for once it was divided into 3 exactly equal parts, which is unusual, and which tells you something about how the committee understood the work. There was no principal author of this discovery. There were 3 separate acts of a single 50-year project, and the committee could not find a reason to rank them. The citation is 1 sentence long. Almost every newspaper in the world reprinted a fragment of it. Here it is in full. The prize was awarded, in the Academy's words, for experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. Read that again slowly, because it has 3 clauses in it, and they are doing 3 completely different jobs. The first clause names the thing they worked with. The second names the thing they destroyed. The third names the thing they built out of the rubble. Most of the coverage that day quoted the first clause, mentioned entanglement, used the phrase spooky action at a distance somewhere in the second paragraph, and left it there. The story that reached the public was simple, and it was this: 3 physicists proved that quantum entanglement is real, and in doing so proved Einstein wrong. That summary is not false. It is just thin enough to be misleading, in the way that saying the Apollo program proved the moon exists is not false. Nobody was seriously in doubt that entanglement was a real prediction of quantum mechanics. The mathematics had said so since the 1930s, and the mathematics had been correct about everything else it had ever been asked. And Einstein, whatever you may have been told, never claimed that quantum mechanics made false predictions. He never claimed entanglement would not be observed. His objection was something much stranger and much more careful than that, and we will spend a good part of tonight on it, because until you understand what Einstein actually said, the prize makes no sense at all. There is another oddity in the announcement that is worth holding on to. The work being honoured was old. The first of the 3 experiments was published in 1972. The second was published in 1982. The third strand, Zeilinger's, ran through the late 1990s and the 2000s. By the time the Academy called Vienna and Paris and California on that October morning, the youngest piece of the work was well over a decade old, and the oldest piece was 50 years old. The Nobel Committee is often slow. It is not usually that slow. Something had to happen before the prize could be given, and it happened much later than the experiments did. Keep that in mind. It is part of the answer. So here is the question I want to put in front of you, and I am going to leave it standing, unanswered, for most of the next 2 hours. What exactly did these three men prove? Not the headline version, the real one. What was on the table before 1972 that was gone by 2015? What did the world lose? I can tell you now that the answer is not that entanglement is real, and I can tell you that the answer is not that Einstein was wrong, at least not in the way that phrase suggests. The answer is stranger, and it is more specific, and it has a shape that most people never quite get told. By the end of tonight, you will know exactly what these three men eliminated from the list of ways the universe could possibly work. You will also know why, having eliminated it, physics still cannot agree on what is left standing. That second part is the piece that almost never survives the trip into a news story, and it is the piece that makes this the strangest prize the Academy has given in a very long time. To get there, we have to go backwards. We are going to go back to 1935, to a 4-page paper by three men in Princeton that was ignored, then to a small journal in 1964 that folded 4 years later, then into a basement laboratory in Berkeley, where a man who wanted to overturn quantum mechanics spent 200 hours proving it right, then to an optical bench in a suburb south of Paris, where a switch flickered 50 million times a second, and finally to a diamond in a laboratory in Delft, and to the light of a quasar that left its galaxy 12 billion years ago and ended its journey deciding the angle of a piece of glass. But before any of that, we have to start somewhere much simpler. We have to start with something so obvious that you have never once in your life thought to question it, because that is the thing that died. And you cannot feel the loss of something until you have first felt how solid it was. So let us begin with 2 boxes. Imagine that I hand you 2 balls. One of them is black and one of them is white, and apart from the color, they are identical. Same weight, same size, same smooth, cool surface under your fingers. Now close your eyes. Keep them closed while you shuffle the 2 balls between your hands, the way you would shuffle a coin from palm to palm, until you have genuinely lost track of which is which. Then, still with your eyes closed, put 1 ball into each of 2 identical boxes and seal them. You have not looked. Nobody has looked. One of those boxes we are going to put on a rocket and send to the moon. The other one stays here, on the table beside your bed. Now think carefully about what is true right now, while both boxes are closed. The ball on the moon is either black or white. You do not know which. If somebody made you bet, you would say 50-50, and you would be right to say it, because that is exactly the state of your knowledge. The same is true of the ball beside you. 50-50. 2 boxes, 2 unknown colors, 250,000 miles apart. And then you reach over and you open your box, and the ball inside it is black. Something has just happened that, if you describe it carelessly, sounds impossible. In the instant you saw the black ball on your bedside table, you learned with total certainty the color of a ball on the surface of the moon. Not with high probability, with certainty. A moment before, that ball was a 50-50 proposition. Now it is white, and you know it, and the knowledge arrived instantaneously across 250,000 miles. Did you cause anything to happen on the moon? Of course not. Did any influence, any signal, any effect of any kind, travel from your bedside table to the lunar surface faster than light? Obviously not. The colors were fixed the moment you sealed the boxes, back when your eyes were shut. Nothing changed on the moon when you opened your box. Nothing traveled. You only learned. That sentence is the whole of common sense in 5 words, and I want you to remember it because we are going to come back to it at the very end of tonight, and it is not going to feel the same. Nothing traveled. You only learned. This is not an exotic situation. It is the most ordinary thing in the world, and you have lived inside it all your life without ever giving it a name. If you pack a pair of gloves into 2 suitcases without looking, and one suitcase goes to Tokyo, then the moment the Tokyo traveler finds a left glove, they know something about a suitcase in your hallway. If you tear a ticket stub in half and mail one half to a stranger, the two halves match, and the matching does not require the halves to be in contact. Correlation is not communication. Two things can agree with each other without either of them doing anything to the other, because they were prepared together, and they carried the agreement with them when they separated. Physicists have a name for the picture of the world that this rests on, and it is a picture with exactly two components. It is worth saying both of them out loud, slowly, because in about an hour, one of them is going to be taken away from you, and you will not be told which one. The first component is called realism. Realism says that things have their properties, whether or not anybody is looking at them. The ball on the moon was white before anyone opened the box. It was white while the rocket was in transit. It was white when it was sealed. Its whiteness was a fact about the ball, sitting there in the dark, entirely indifferent to whether any human being ever discovered it. That is realism, and it sounds less like a scientific hypothesis than like a description of what the word thing means. The second component is called locality. Locality says that what you do here does not immediately affect what happens there. If you want to change something on the moon, you have to send something to the moon, and whatever you send takes at least the time light takes to make the trip, which is a little over a second. There are no instantaneous levers. There is no action at a distance. Everything that reaches out has to cross the ground in between. That is locality, and it is not a stray assumption either. It is essentially the content of Einstein's theory of relativity, which says that no cause can outrun light, and which is one of the most exhaustively tested ideas in the history of the subject. Put those two together, and you get a phrase that will run through the rest of tonight, like a thread. Local realism. The world is made of things that have properties, and those things only affect each other by reaching across the space between them at a finite speed. Now, I want to be very careful here, because this is the moment where the story usually goes wrong. Local realism is not naive. It is not the layperson's stumbling guess that a physicist gently corrects. It is a precise, powerful, extraordinarily successful assumption that underpins essentially every scientific explanation given between the time of Newton and the 1920s. Everything you have ever been told about how anything works is a local realist story. The wind pushes the leaf, the current flows through the wire, the gravity of the sun reaches out across 93 million miles at the speed of light and curves the Earth's path. Cause here, effect there. Something in between doing the carrying. So when I tell you that quantum mechanics has a problem with this, I do not want you to hear that quantum mechanics has a problem with some careless folk belief. I want you to hear that quantum mechanics has a problem with the flaw. And here is the crack, and it is a very small one to begin with. Quantum mechanics agrees with every single prediction you would make from the two-box story. Every one. If you set up the quantum version of this experiment and you record what comes out, the pattern of results is exactly what the boxes would have given you. The colors always come out opposite. The individual outcomes always look random. There is no measurement you can make on one side that reveals anything at all about what was done on the other. Quantum mechanics agrees with all of it. What it will not agree with is the story underneath. Let us run it again. Same two boxes, same rocket, same bedside table. But this time, the things inside the boxes are not balls, they are particles. Two photons, say, born in the same event, in the same instant, from the same atom. And the property we are interested in is not color, but polarization, which is simply the direction in which a light wave is wobbling as it travels. Everything about the setup is the same. The two photons are produced together in a way that guarantees their polarizations are opposite. One goes to the moon, one stays here. Nobody has measured either of them. Now open the box. I want you to run this twice in your mind, and I want you to pay attention to the difference, because the difference is not in what you see, it is in what was true before you looked. In the first version, the classical one, you lift the lid and light falls on a ball that has been black this entire time. Your hand knows the weight of the lid. The hinge makes its small sound. Your eye takes in a color that was already there, that was there in the dark, that was there on the launch pad, that would have been there Whether you had opened the box tonight, or in 10 years, or never, you have discovered something. The universe was already holding the answer, and it handed it over. In the second version, the quantum one, you lift the same lid, your hand feels the same weight, the hinge makes the same small sound, and light falls on a photon whose polarization, according to the mathematics that has never once been wrong about anything, did not exist until the moment the light fell on it. Not unknown, not hidden, not written down somewhere you could not read, undecided. And in that same instant, 250,000 miles away, in a sealed box that nobody is anywhere near, the other photon stops being undecided too, and takes the opposite value. Same gestures. Completely different world. This is the point at which people quite reasonably say, hold on, how could you possibly tell those two situations apart? In both cases, you open a box and find a definite answer. In both cases, the far particle turns out to be the opposite. If the outcomes are identical, what on earth is the difference between saying the color was there all along and saying it came into being when you looked? Is that not just a matter of taste? Is it not, in fact, philosophy rather than physics? That objection is a good one. It is so good that it held the field for 30 years, and I'm going to ask you to hold on to it, because the entire story of this Nobel Prize is the story of that objection being wrong in a way nobody saw coming. But first, let us be clear about why anybody would propose the second version at all, because on the face of it, it is the more expensive story. It is weirder. It requires more explaining. Why not just say the properties were there and quantum mechanics does not happen to mention them? The answer is that the mathematics does not leave room for them. A quantum system is described by an object called the wave function. It is not a picture of the particle. It is a mathematical object that, when you handle it correctly, gives you the probability of every possible outcome of every possible measurement you might make. The wave function evolves in time according to the Schrödinger equation, and that evolution is completely smooth, completely deterministic, and completely free of any mention of specific values. The equation does not track where the particle is. It tracks the shape of the possibilities. And here is the crucial part. When two particles interact and become entangled, quantum mechanics does not give you two wave functions. It gives you one for the pair, and that single joint wave function contains information about the relationship between the two particles and no information whatsoever about either particle on its own. It says, whatever these two turn out to be, they will be opposite. It does not say what either of them is. There is no line in it where the value is stored. The correlation is written down in full, and the values are simply absent. Then a measurement happens, and the wave function collapses, and definite values appear where there were none, on both sides at once. It is worth pausing on that word, undecided, because it is doing an enormous amount of work, and it is easy to hear it as a softer word than it is. When a physicist says a photon's polarization is undecided, they do not mean that the photon has a polarization which is currently unmeasured. They mean that the photon is in a state called a superposition, in which the mathematics assigns it a share of every possible answer at once, and in which the individual answers have no separate existence to be found. The proof that this is not just fancy language for ignorance is that superpositions interfere with each other. If a particle really had one definite value all along, and you were simply unaware of it, the possibilities you were ignorant about could not combine, cancel, and produce patterns. They do. That interference is measurable. It is the basis of every experiment in the subject, and it is the reason nobody can quietly replace superposition with a shrug. There is one more thing about entanglement that gets lost in the two-box picture, and it matters later. An entangled pair is not two objects with a relationship. Mathematically, it is one object with two ends. You cannot write down a description of one photon by itself, hand it to somebody, and have them be able to predict anything the photon does. There is no such description. The only complete description is of the pair, and it stays a single description no matter how far apart you drag the two ends of it. That is why the ordinary language of here and there begins to strain. The thing you have separated by 250,000 miles was never, in the mathematics, two things. So for our two quantum balls to have known their own colors the whole time, There would have to be extra information about them that the wave function does not contain. Some additional bookkeeping, riding along with each particle, that says, I am the black one. That extra bookkeeping has a name. It is called a hidden variable, and a theory that includes it is called a hidden variable theory. That is what Einstein wanted, not a different theory of atoms, not a rejection of quantum mechanics, just the hidden variables. He thought the wave function was an honest but incomplete description, in the way that a weather forecast is an honest but incomplete description of the atmosphere. 70% chance of rain is a perfectly good statement, and it is not a claim that the sky is currently in a 70% state. It is a statement about what you know. Einstein thought the wave function was exactly like that, and that underneath it there were facts. Niels Bohr, and with him most of the physics establishment, said no. The wave function is not a summary of your ignorance. It is the whole thing. There is nothing underneath. Asking what a photon's polarization was before you measured it is not a hard question. It is not an open question. It is a question with no content, like asking what is north of the North Pole. And here is where the trouble sat for 3 decades. 2 stories. One says, the values are there, and quantum mechanics is silent about them. The other says, there are no values until you look. Both stories predict identical experimental results in every experiment anybody could think of. There is no measurement, none, that distinguishes a hidden fact you have not learned from a fact that does not yet exist. Or so everybody believed. The consensus that formed around this was not that the question had been answered. It was that the question could not be answered, ever, by any experiment, and that a question which cannot be settled by experiment is not a physics question. It belongs to philosophy, and philosophy departments are down the hall. That judgment hardened into something close to a professional taboo, and it lasted from the middle of the 1930s until the middle of the 1960s, and it is the reason that a 50-year-old set of experiments won a prize in 2022. But before we get to the taboo, we have to meet the man who provoked it. And he was not some fringe figure at the edge of the subject. He was the most famous scientist alive. In May of 1935, the journal Physical Review published a paper, 4 pages long, with 3 authors, and a title that was a question. The title was, Can Quantum Mechanical Description of Physical Reality be Considered Complete? The authors were Boris Podolsky, Nathan Rosen, and Albert Einstein. Their answer was no. The argument they made is the 2-box argument, and it is worth walking through slowly, because almost everything you have heard about Einstein and quantum mechanics is a garbled version of it. Start with 2 particles that interact and then fly apart. Because they interacted, quantum mechanics describes them with a single joint wave function, and that wave function fixes the relationship between them. Whatever one is, the other is the opposite. Now let them separate as far as you like. A room, a continent, a light year. Nothing in the mathematics cares. Now measure the first particle. You get an answer. And because of the correlation, you can now predict with absolute certainty what a measurement on the second particle will give, without going anywhere near it, without touching it, without disturbing it in any way. Einstein, Podolsky, and Rosen then applied a principle they stated explicitly in the paper, and which they clearly regarded as beyond argument. If, without in any way disturbing a system, you can predict with certainty the value of a physical quantity, then there must exist something real corresponding to that quantity. That is their criterion of physical reality. And if you strip the formality of it, it says this: if you can be sure what you would find, then there is something there to find. Apply that to the second particle. You have predicted its value with certainty. You did not touch it. Therefore, by their criterion, that value is real. It is a fact about the second particle. It was a fact before you did anything. And now the trap closes. Because quantum mechanics does not contain that fact, the wave function has no line in it where that value is written. So one of 2 things must be true. Either the description is incomplete, or measuring the first particle somehow reached across the gap and made something happen to the second. That second option is the one Einstein could not swallow. He would later give it a name that has outlived every other phrase in this story. Writing to his old friend Max Born, In a letter dated the 3rd of March, 1947, he called it spookhaft Fernwirkung, spooky action at a distance. It is worth knowing that the phrase is not in the 1935 paper at all. The paper is written in flat, formal, almost bureaucratic language. Spooky action at a distance is Einstein in a letter, 12 years later, still unable to let it go. So Einstein took the other option. The description is incomplete. The particles carried their values with them. Quantum mechanics simply does not record those values. And one day, a deeper theory will. I want to make sure this lands correctly, because it is routinely mangled. Einstein was not saying quantum mechanics was wrong. He was not predicting that its calculations would fail. He was not confused about the mathematics. He had helped build the subject and had a Nobel Prize of his own for the photoelectric effect, which is one of the founding results of quantum theory. What he was saying was that quantum mechanics is a correct theory of probabilities that is silent about the underlying facts, and that a theory silent about the underlying facts cannot be the final word. The weather forecast comparison is the honest one. If your forecast says 70% chance of rain tomorrow, the forecast is not wrong when it rains. It was a good forecast, but nobody thinks the atmosphere is in a 70% state. The atmosphere is doing something perfectly definite. The 70% is a statement about the forecaster. Einstein thought the wave function was a forecast, and that behind it there was weather. There is a small human detail here that I find hard to leave out. Einstein was not entirely happy with his own famous paper. Podolsky wrote the actual text, and did it, apparently, without showing Einstein a final draft before submission. Afterwards, Einstein complained, in a letter to Erwin Schrödinger, that the essential point had been buried in erudition, which is a very polite way of saying that his co-author had made it too complicated. For the rest of his life, Einstein preferred his own later, simpler versions of the argument to the one the world remembers. Schrödinger himself responded to the paper the same year, and in doing so, he gave the phenomenon the name it still carries. In German, he called it Verschränkung, in English, entanglement, and he did not treat it as a curiosity. He wrote that it was not one but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Schrödinger, in other words, saw immediately that this was not a footnote. It was the thing itself. The same year, and in the same frame of mind, he invented the cat. Niels Bohr replied in October. He published in the same journal, and he used the identical title, word for word, which is about as direct a response as physics permits. Bohr's reply is famously difficult. Even physicists who agree with its conclusion have described it as more assertion than argument, and there is a long tradition of people admitting privately that they are not sure what parts of it mean. Its core, as far as anyone can reconstruct it, is that Einstein's criterion of physical reality contains a hidden assumption. When Bohr says that measuring one particle does not disturb the other, he does not accept that the word disturb has been properly defined. In quantum mechanics, what you can meaningfully say about a system depends on the whole experimental arrangement, and you cannot cut the arrangement in half and treat one particle as an independent object with its own properties. The pair is the thing. Asking about one half of it, in isolation, is asking a question the theory does not have a place for. It also helps to know that 1935 was not the opening of this argument. It was closer to the end of it. Einstein and Bohr had been at each other for the better part of a decade by then, most famously at the Solvay conferences in Brussels, where Einstein would arrive at breakfast with a thought experiment designed to break the uncertainty principle, and Bohr would spend the day dismantling it and present the wreckage by dinner. In 1930, Einstein produced his best one. Imagine a box full of light, with a shutter and a clock, sitting on a spring balance. Open the shutter for a precisely timed instant. Let a single photon escape, and weigh the box, before and after. Mass is energy, so weighing the box tells you the photon's energy exactly, and the clock tells you the time of emission exactly, and the two together are not supposed to be simultaneously available. Bohr, by his own account, had a terrible night. In the morning he answered it, and he answered it using general relativity. The box recoils in the gravitational field as the photon leaves, And a clock that changes height in a gravitational field runs at a different rate. And when you work through the size of that effect, it restores the uncertainty exactly. Bohr had beaten Einstein using Einstein's own theory. That episode matters for the story we are telling because it explains the atmosphere of 1935. By then, Einstein had lost this fight publicly, twice, in front of everybody who mattered. And after 1935, his complaint changed character. He stopped trying to show that quantum mechanics was internally inconsistent, which is what the photon box had been aiming at, and started saying something much harder to attack and much easier to ignore, that the theory was fine and incomplete, and that being satisfied with it was a failure of nerve. Ignoring it was made easier by where Einstein was standing. He spent his last 20 years at the Institute for Advanced Study in Princeton, working on a unified field theory that never came together, increasingly regarded within the profession as a great man who had wandered off the main road. He knew it. He wrote to Born that he must seem to younger colleagues like an obstinate old heretic, and in another letter, with more edge, that he could not believe God plays dice, and got back from Born's circle the fair reply that it was not for Einstein to tell God what to do. What he never got was an experiment. He died on the 18th of April, 1955, in Princeton Hospital, 9 years before anybody worked out that his objection could be tested at all, and 67 years before 3 men collected a Nobel Prize for testing it. Whether or not you find that convincing, and generations of physicists have gone back and forth, one thing is clear about what happened next. Bohr won, not by argument, and not because his paper settled anything. He won because quantum mechanics kept working, and it worked spectacularly. Over the following 2 decades, the theory explained the structure of the periodic table, the behavior of metals and semiconductors, the mechanism of the laser, the physics of the transistor, the chemistry of every bond in your body, and eventually the interactions of particles to a precision of 10 or 12 decimal places, which remains the most accurate agreement between prediction and measurement anywhere in science. A theory delivering that is not going to be dislodged by a philosophical objection from a man in his 50s, however famous he is. So the question did not get answered. It got outrun, and there is a particular kind of damage that does, because a question that has been outrun rather than answered does not stay open in a healthy way. It closes. Quietly, without a decision, without anybody voting on it, and often without anybody noticing that a real question is being treated as a settled one. What happened next was not a debate. It was a silence, and it lasted 30 years. There is a version of the history of science in which good questions stay open until somebody answers them. That version is comforting, and it is not true. Questions close for all sorts of reasons that have nothing to do with evidence. They close because the people who could work on them cannot get funding. They close because a supervisor says it will ruin your career, and the supervisor is right. They close because a proof appears which turns out, decades later, to have a hole in it that nobody checked because checking it was not worth anybody's time. All 3 of those things happened here. Start with the proof. In 1932, 3 years before the Einstein-Podolsky-Rosen paper, the mathematician John von Neumann published a comprehensive formal treatment of quantum mechanics. It is a magnificent piece of work, and it is still cited. Inside it, von Neumann included a theorem which appeared to demonstrate that hidden variable theories were impossible, not unlikely, not unsupported, mathematically ruled out. If von Neumann was right, then Einstein's entire position was not merely unfashionable, it was incoherent, and there was no point anybody spending a career on it. Von Neumann's reputation was enormous, the book was in German, the proof was technical, and the conclusion was extremely convenient for the prevailing view. So it was not checked carefully, it was cited. It was wrong. Not in its mathematics, which is fine, but in one of the assumptions it fed into the mathematics. Von Neumann had assumed a property that no sensible hidden variable theory needs to have, and having assumed it, he had of course found that theories with it were impossible. It is the intellectual equivalent of proving that no animal can fly, after quietly assuming that all animals have 4 legs. The person who found this was a German mathematician and philosopher named Greta Hermann. She published her critique in 1935, the same year as the Einstein paper, and she identified the flawed assumption precisely and clearly. Her work went essentially unread. She was a woman, working outside the physics mainstream, publishing in a philosophy journal in Germany in 1935, which is about as many strikes as history can arrange against a single paper. The flaw she found would not be rediscovered and made famous for another 31 years. Now the second thing that happened, which is the career damage. In 1952, a young American physicist named David Bohm did something everybody knew was impossible. He constructed a working hidden variable theory. It reproduced every prediction of standard quantum mechanics exactly, and it did it while giving particles definite positions at all times, guided by a wave that pushed them around. The idea was not entirely new. Louis de Broglie had proposed something similar in 1927 and had abandoned it after a rough reception at that year's Solvay conference. Bohm rebuilt it properly and published in 2 papers. If you want to understand the reception, understand where Bohm was when he wrote it. He had been a graduate student under Robert Oppenheimer at Berkeley. In 1949, he was called before the House Un-American Activities Committee, and he refused to testify against his colleagues. He was arrested, acquitted, and then quietly unemployable. Princeton did not renew his contract. His passport was taken. He left for Brazil, and it was in Sao Paulo, in effective exile, cut off from the community he had grown up in, that he wrote down a theory that Einstein himself had thought could not exist. It is worth sitting inside that for a moment, because it is the human center of this part of the story. Picture a small apartment in Sao Paulo in 1952. It is hot in a way that a man raised in Pennsylvania and trained in Berkeley has no defense against. He does not have his passport. The United States consulate took it and told him he could have it back if he returned home, where he would be arrested again. He is 34. The letters from Princeton have stopped. The journals arrive weeks late when they arrive. He is teaching in a language he is still learning, to students who have never heard of him, in a department with almost no equipment. And in the evenings, at a desk in that heat, he is writing down a complete alternative account of quantum mechanics, in which particles are real and have positions and are pushed around by a wave, and in which every prediction of the standard theory comes out identical. He finishes it, he sends it to physical review. It is published. And then, for the next 30 years, almost nothing happens, except that his name becomes a slightly awkward thing to mention at conferences. The word for what the physics community did to Bohm's theory is not refutation, and it is not even rejection. It is neglect, which is more effective than either. The response from the physics establishment was not refutation. It was dismissal. The theory was called unnecessary, ugly, a step backwards. Einstein, of all people, was unimpressed, calling it too cheap a solution, because Bohm's theory bought its definite values at the price of an explicitly instantaneous connection between distant particles, which was exactly the thing Einstein was trying to avoid. Bohm had escaped the trap by opening the door Einstein had spent 20 years trying to nail shut. And here is the point. Bohm's theory existed. It worked. It made every prediction quantum mechanics made. Its existence should, by itself, have ended the belief that hidden variables were impossible, because there was one, in print, functioning. Instead, the profession went on repeating that von Neumann had ruled them out. It is genuinely difficult to reconstruct how a field holds 2 contradictory things in its head for that long. And the honest answer is that almost nobody was paying attention, because paying attention had no reward attached to it. Which brings us to the third thing, and the largest, which is a phrase. Shut up and calculate. It is usually attributed to Richard Feynman, though the physicist David Mermin, who actually coined it in print, later admitted it was his own. Either way, it captured the working culture of physics for about 40 years, and it was not a joke. It was advice. The theory works. The numbers come out right to more decimal places than you can measure. Your job is to use it, not to ask what it means. And if you ask what it means, you will produce no results, you will publish nothing, and you will not get tenure. It helps to understand that Copenhagen was not merely a set of ideas. It was a place, and a network, and a rite of passage. Bohr's Institute on Blegdamsvej in Copenhagen was where the young talent of European physics went in the 1920s and 30s to be formed, and they came back to their own countries, carrying not only the mathematics, but Bohr's way of talking about it, his particular refusal to answer certain questions, his insistence that the questions themselves were malformed. Heisenberg came out of there, Pauli, Landau, Gamow. When a generation of the most gifted people in a field are all trained in the same building by the same man, the resulting consensus is not a conclusion anybody argued their way to, it is a dialect. And dialects are enforced socially rather than logically. There are stories, some of them well documented, of physicists who raised foundational questions at seminars and were told, publicly, that they had misunderstood the theory, when what they had actually done was ask what it meant. The safe move was to stop. Most people made the safe move, and there is no reason to think worse of them for it. They had families and jobs. That is not a conspiracy. It is something more ordinary and more effective than a conspiracy. It is an incentive structure. Nobody had to forbid the question. They simply had to make sure that asking it cost you your equipment time, your funding, your students, and your seat at the table, and the question went away on its own. For 30 years, from the middle of the 1930s to the middle of the 1960s, that is what the field looked like. Quantum mechanics conquered chemistry, solid-state physics, nuclear physics, and eventually electronics. The transistor arrived in 1947. The laser arrived in 1960. Every one of those achievements made the foundational question look smaller and more irrelevant. Why would anyone stand at the base of a building this successful and ask whether the foundations were properly understood? And underneath all of it, unexamined, sat the two-box question. Are the properties there before you look, or not? Not answered, not disproved, not tested, just filed under philosophy and left in a drawer for a generation, while the world was quietly rebuilt on top of it. The man who took it back out of the drawer was not a philosopher, and he was not a foundation specialist, because in 1964 there was almost no such thing. He designed particle accelerators for a living. He worked on this in his spare time on a year's leave, and he published it in a journal that was about to go out of business. John Stuart Bell was born in Belfast in 1928 into a family with no money for education past the age of 14. He got to university on scholarships and a technician's job in a physics department, where he spent his days cleaning glassware and setting up demonstrations and reading the textbooks in the evenings. He ended up at CERN, in Geneva, designing particle accelerators. That was his profession. He was very good at it. The foundations of quantum mechanics were his hobby. He said so himself, without any false modesty about it. This was the thing he thought about on holiday, on trains, in the evenings, in the small hours. He had been bothered since he was a student by the way the subject was taught, by the sense that he was being told to stop asking somewhere before the questions had run out. He described being told, essentially, that his objections were philosophy and he did not accept it. In 1963, he took a year's leave from CERN and went to the United States, first to Stanford, then to Wisconsin and Brandeis. In that year, with time on his hands and no accelerator to design, he wrote 2 papers. The first one he wrote is the one that came out second. It is a careful, respectful demolition of von Neumann's impossibility proof. Bell found the same flawed assumption Greta Hermann had found 31 years earlier, and he found it independently, and he explained exactly why it was too strong to be required of any real, hidden variable theory. He sent the paper off in 1964. An editor moved offices, or moved journals, and the manuscript was misplaced. It sat lost for 2 years, and was finally published in Reviews of Modern Physics in 1966. By which point the second paper had already been out for 2 years and made the first one look like a follow-up. The second paper is the one that matters. Bell wrote it after clearing the ground, having satisfied himself that hidden variables were not impossible after all, and having read Bohm's theory closely enough to notice the thing that everybody else had used as an objection, that Bohm's hidden variables required an instantaneous connection between distant particles. Bell asked the question nobody had asked. Was that a flaw in Bohm's particular theory, or was it unavoidable? If you insisted on hidden variables, and you also insisted on locality, could you build a theory at all? He published the answer in 1964 in the first volume of a brand new journal called Physics Physique Physica. The journal had been set up to pay its authors, which was unusual and rather noble. It ran for 16 issues and folded in 1968. By an enormous margin, Bell's 4-page paper is the most cited thing it ever printed, and it is fair to say that the journal is remembered today for precisely one reason. Here is what he did. Take the two-box setup, two particles, produced together, flying apart. On each side there is a measuring device, and each device can be set to one of two settings. Think of the setting as an angle. You can turn the polarizer to point one way or another way, and each measurement gives one of two answers. Call them yes and no. Now suppose the world is locally real. Suppose the particles carry their answers with them, prepared at birth, and that nothing you do on one side affects the other. Then, each particle must arrive carrying a full set of instructions. If you are asked at this angle, answer yes. If you are asked at that angle, answer no. It does not matter how the instructions were generated, how complicated they are, how many hidden variables there are, or whether the instructions are random. The only thing that matters is that they exist before the measurement, and that they do not depend on what is being asked on the other side. It is worth making the instruction set picture concrete, because it is the heart of the theorem, and it is not hard. Imagine that instead of particles, you are sending out pairs of identical twins from a room, and before they leave, the twins agree on how they will answer 3 possible questions. Not by signaling later. They cannot signal later. They simply decide in advance. Question 1, yes. Question 2, no. Question 3, no. Both twins leave carrying the same agreed sheet, or opposite sheets, whichever the game requires. Now send them to opposite ends of the country. An interviewer at each end picks one of the 3 questions at random and records the answer. Because the twins agreed in advance, and because there are only so many ways to fill in 3 yes or no boxes, there are hard limits on how often the 2 ends can agree and disagree across the various pairings of questions. Those limits do not depend on how clever the twins are. Cleverness is already included. Any strategy at all is just another sheet. The limits come from the fact that the answers exist on paper before the questions are asked. You can run the numbers on the back of an envelope, and when you do, you find you cannot get agreement patterns above a certain level no matter what you write on the sheets. Bell's achievement was to notice that entangled particles beat the envelope. There is no sheet. There is no strategy. Whatever the particles are doing, they are producing patterns of agreement that no pre-written sheet can imitate. Bell then did something that looks, the first time you see it, like a card trick, and which on the second look is one of the most elegant pieces of reasoning in 20th century physics. He worked out the arithmetic constraints that any such set of instructions must obey. Not for a particular theory, for all of them. Every conceivable local hidden variable theory, including ones nobody has invented yet, including ones we would find repulsive, including ones with 1 trillion hidden variables and rules of unimaginable complexity. If the instructions are carried with the particles, and if the instructions on one side do not depend on the question asked on the other, then when you run the experiment many times and count how often the 2 sides agree, at various combinations of settings, and you combine those counts in a particular way, the resulting number is bounded. There is a ceiling. In the version physicists actually use in laboratories, that ceiling is the number 2. I want you to hold on to that, because we are going to be watching that number for the rest of tonight. A number that cannot go above 2. Now here is the sting. Quantum mechanics, if you sit down and calculate what it predicts for this same experiment, does not respect the ceiling. It predicts a value that goes above 2. The 2 theories, which had agreed about absolutely everything for 30 years, disagree here, and they disagree by a specific, calculable, measurable amount. The reason they disagree comes down to the shape of a curve. When you ask how often 2 entangled particles agree as a function of the angle between the 2 measuring devices, quantum mechanics gives you a smooth curve, the cosine of twice the angle. A local hidden variable theory, restricted to carrying instructions, cannot produce that curve at those angles. The best it can do is something that runs in a straight line between the same endpoints. The curve and the straight line touch at the ends and separate in the middle. The violation of Bell's inequality is, quite literally, the gap between a curve and a chord. Sit with what that means. For 30 years, the argument between Einstein and Bohr had been treated as a matter of taste, of temperament, of what you found philosophically comfortable, precisely because no experiment could tell them apart. Bell found the experiment, and he found it without needing to know what the hidden variables were, without needing to invent a rival theory, without needing anybody's permission about what reality means. You do not have to measure the hidden information. You only have to count coincidences and add up a number, and if the number is bigger than 2, then no set of pre-carried instructions could have produced your data. None, ever. A metaphysical question had become arithmetic. There is one more feature of the theorem worth stating plainly, because it is what gives it such reach. Bell's argument never mentions quantum mechanics until the very last step. Everything before that is about instruction sets and counting. This means the inequality is not a prediction of quantum theory that could be overturned if quantum theory were replaced. It is a constraint on a whole class of explanations, and it will still be a constraint in 100 years when quantum mechanics has been superseded by whatever comes next. If nature violates it, then no local, property-carrying account of nature can ever be written by anybody at any time, using any physics. That is a very unusual kind of scientific statement. Most results close a door. This one closes a corridor. You might imagine that this landed like a bomb. It did not land at all. The paper was published in an obscure journal on a subject that had been professionally dead for a generation by a man whose day job was accelerator design, and for 5 years it was read by almost nobody and cited by almost nobody. Bell went back to Geneva and went back to work. The experiment he had made possible required a source of entangled particles, 2 measuring devices with switchable settings, detectors sensitive enough to catch individual photons, timing electronics good enough to tell which detections belonged together, and someone willing to spend years of their life on a question the field had agreed was not a question. For half a decade, nobody volunteered, and then somebody found the paper in a library by accident while working on something else entirely. John Clauser was a graduate student at Columbia University in the late 1960s, working on a thesis in radio astronomy under Patrick Thaddeus. His subject was the cosmic microwave background. It had nothing whatsoever to do with quantum foundations. He came across Bell's paper in the library. Accounts differ slightly on exactly how, and Clauser himself has told it more than one way over the years, but the shape is consistent. He was reading around the edges of his field. He found this 4-page thing in a journal nobody had heard of, and he could not put it down. He had already been troubled, as a student, by the same feeling Bell described, that the standard account of quantum mechanics stopped answering somewhere before it had finished. And here was a paper saying that the place where it stopped answering could be walked into with equipment. He decided to build the experiment. There is a detail about Clause's motivation that is important and that gets left out of most tellings because it complicates the hero's story. He was not trying to confirm quantum mechanics. He was hoping to break it. He believed, or at least strongly suspected, that the hidden variables were there, that Einstein had been right, and that the reason nobody had run this experiment was that the establishment did not want it run. He was going into the laboratory, looking for the result that would overturn the orthodoxy. In 1969, he wrote to 3 people, John Bell, Louis de Broglie, and David Bohm. All 3 were, in one way or another, dissidents. Bell wrote back. And what he told Clauser is one of the quietly devastating facts of this whole story. Clauser's letter was the first response of any kind that Bell had ever received about the 1964 paper, 5 years in print, 1 letter. That same year, Clauser published a paper with 3 collaborators, Michael Horn, Abner Shimony, and Richard Holt, in Physical Review Letters. It is titled Proposed Experiment to Test Local Hidden Variable Theories, and it is universally known by the initials of its 4 authors, CHSH. There is a small piece of decency buried in how that paper came to exist. Clauser had worked out that a real experiment was possible and had submitted an abstract about it to a meeting. Independently, and at almost the same time, Abner Shimony at Boston University had set his own graduate student, Michael Horn, on exactly the same problem, and they had reached the same conclusion. Shimony found out about Clauser's abstract and faced the ordinary academic choice: race him or call him. He called him. The four of them agreed to write it as one paper rather than two, with Richard Holt, who was building an experiment at Harvard, joining as the fourth. In a field where priority disputes have ended friendships and occasionally careers, four people who could have fought over this decided to share it, and the result is the inequality that every laboratory on Earth still uses. What it did was take Bell's inequality, which had been written for an idealized experiment with perfect detectors and perfectly correlated pairs, and rewrite it into a form that a real laboratory could actually use. The CHSH version measures a quantity conventionally called S, built out of 4 correlation measurements at 4 combinations of settings. In any locally real world, the size of S can never exceed 2. Quantum mechanics, at the right angles, predicts about 2.8. So now there was a target: get S above 2, and every local, property-carrying account of nature dies at once. Clauser then went looking for somebody who would let him try, and this is where he ran into the wall the previous part of this story built. He took the idea to Richard Feynman. Feynman was, by 1969, the most admired physicist alive, a Nobel laureate, the man who had rebuilt quantum electrodynamics and made it work to a dozen decimal places. Clauser has described what happened next many times, and his version is that Feynman threw him out of the office. Caltech's own account of the episode, published decades later when Clauser won his own prize, is only slightly softer. Feynman was highly offended by the proposal and told Clauser that attempting the experiment was tantamount to professing a disbelief in quantum physics. Quantum mechanics, in Feynman's view, was obviously correct. It needs no further testing. That was the verdict, from the best in the business, and it was not eccentric. It was the mainstream position, stated crisply by the person best qualified to state it. Remember that sentence. We will come back to it at the end of tonight, and by then it will have a very different weight. Clauser did not stop. In late 1969, he took a postdoctoral position at Berkeley, and there he found the two things he needed: equipment he could adapt, and senior people willing to look the other way. Charles Townes, who had shared the 1964 Nobel Prize for inventing the maser and the laser, agreed to let Clauser spend half his time on the Bell experiment. Howard Shugart and Eugene Commins made room for him. Nobody was enthusiastic. They were tolerant, which in the circumstances was a great deal. He was given a graduate student, Stuart J. Friedman, and together they built it. Picture the room. It is a basement laboratory at Berkeley in 1971. In the middle of the bench, there is a small oven with calcium in it, heated until the metal vaporizes and drifts out as a thin beam. Above the beam sits an arc lamp, a hard, ultraviolet-rich light that hurts to look at, and the lamp's job is to hit the calcium atoms and knock their electrons up into a particular excited state. The atoms do not stay there. They fall back down in 2 steps, and each step releases a photon. The first photon comes out green at 551.3 nanometers. The second comes out violet at 422.7 nanometers. And because the atom's total angular momentum was 0 before the cascade and 0 after it, and angular momentum is conserved, those 2 photons must between them carry away nothing, which means their polarizations are locked to each other. That is the source. An atom, falling downhill twice, throwing out a matched pair. Now, follow the pair. They fly out in opposite directions along the bench, and there is not much bench. The 2 detectors sit roughly 1.5 meters apart, which is nothing, which is closer than you are to the far wall of the room you are in. Each photon runs into a polarizer, which in 1971 means a stack of 10 glass plates set at a precise angle, and then into a photomultiplier tube, which is a device that can register the arrival of a single photon by turning it into an avalanche of electrons. Behind that sits a coincidence circuit, waiting to see two detections close enough together in time to have come from the same atom. The physics of what those glass plates are doing is worth one sentence, because it is the whole measurement. A polarizer asks a photon a question with only two possible answers. Are you aligned with this direction? Yes or no. It cannot ask anything subtler, and there is no third outcome. Turn the polarizer, and you have asked a different question. That is why the settings matter so much, and why the experiment lives or dies on being able to change them. The entire theorem is about what happens when the two ends ask questions that do not match. And the counting is genuinely brutal. Most of the photons never make it. The polarizers of the day lost light. The photomultipliers of the day converted only a small percentage of arriving photons into a countable signal, and the cascade itself sprayed its pairs in all directions, of which only a narrow cone was ever going to reach a detector. Out of every 10,000 pairs the calcium produced, the experiment saw a handful. That inefficiency will come back later in this story as a serious problem with a name. In 1971, it was simply the reason the work took months. And then you wait. The rate at which useful pairs arrive is a few tens per minute, on a good day. The polarizer settings have to be changed by hand. Clauser and Friedman ran that apparatus in those conditions for around 200 hours of accumulated data. Not 200 hours in a week, 200 hours of counting, spread across months, in a basement, on a question the discipline had agreed was philosophy. And slowly, event by event, the number climbed. The quantity they tested was a simplified single-parameter form of the inequality, now called Friedman's inequality, in which a certain difference has to be 0 or less if the world is locally real. They measured it at 0.050, plus or minus 0.008, 6 standard deviations above the ceiling, in agreement with quantum mechanics, in conflict with local realism. The paper appeared in Physical Review Letters on the 3rd of April, 1972. That is the first time in the history of our species that anybody checked whether the world has definite properties when nobody is looking at it. The answer came back, no. Two things about that moment deserve to be said out loud. The first is that Clauser lost. He had gone in hoping for hidden variables. He had a standing wager on it. He has said, since, more than once, and without much softening, that the result was the opposite of what he wanted, and that it stayed a disappointment for years afterwards. There is something clean about that which I do not want to rush past. He built an instrument to prove himself right. The instrument told him he was wrong, and he published it anyway, in full, immediately. That is the entire method, in one person, working exactly as advertised, and it is rarer than it should be. The second thing is harder. The name on that paper, first, before Clauser's, is Stuart J. Friedman. He was the graduate student. He built it, ran it, and took the data. The inequality they tested carries his name. He went on to a long career in nuclear and particle physics at Berkeley, and he died in November of 2012 at 68 years old. The Nobel Prize is not awarded posthumously, and it cannot be split more than 3 ways. So when the Academy called Berkeley's part of this story, in 2022, 50 years after the fact, the first Bell test in history had exactly one living author to call. Whatever else the prize was, it was a photograph of a moment with people cropped out of it. Friedman is one of them. There are others we will meet. And there is one more problem, which is worse, and which nobody wanted to hear. Within a year of the Berkeley result, the man who had made it possible stood up and explained why it did not settle the question. John Bell had spent 8 years waiting for somebody to run his experiment. When somebody finally did, and the result came out in favor of quantum mechanics and against the local realism he personally hoped would survive, he did the thing that tells you what kind of scientist he was. He pointed out why the experiment was not good enough. It is worth stopping on Bell here, because this is the moment that defines him. He had waited 8 years. The experiment had finally been done. Its result was going to make his paper famous, and it did. The easy move, the human move, was to accept the victory and let the caveats be somebody else's problem in 10 years. Instead, he stood up and said, in effect, This does not prove what you think it proves. And here is exactly where my own theorem is weaker than it looks. He also, and this is the part people find hardest to believe, wanted the experiments to fail. Bell said so repeatedly and in public. He hoped that quantum mechanics would break down at large separations, that the correlations would fade with distance, that there would turn out to be a sensible local world underneath after all. He described the alternative, in a BBC interview in 1985, in terms that were close to grief, that the cheapest way out was to suppose the universe is a kind of clockwork in which nothing is genuinely free, and that he did not believe it, and that the real trouble was that Einstein's program fails. So the man who made the question testable spent his career hoping the answer would come back the other way, and spent it sharpening the tests anyway. That is not a small thing. The problem he identified is subtle, and it is fatal, and once you see it, you cannot unsee it. In the Berkeley experiment, the polarizers did not move. They were set to an angle by hand. The apparatus was run for hours, and then they were set to a different angle and run again. Which means that, at the moment each pair of photons was created inside that calcium atom, the questions those photons were going to be asked had already been decided, and the answers were sitting there in the room, physically embodied in the orientation of two stacks of glass. Now, that sounds harmless. But remember what the theorem assumes. It assumes that the instructions carried by the particles cannot depend on which question is going to be asked. If the settings are fixed in advance, in the same room, connected to the source by ordinary physics, then in principle there is a channel. Some influence, however implausible, could run from the polarizer's orientation back to the atom, and the photons could leave the atom already knowing how they were going to be interrogated. A pair of photons that knows the questions in advance can carry a set of instructions that imitates quantum statistics perfectly while still being entirely local and entirely real. That is not paranoia. It is the honest reading of what the theorem does and does not cover. Bell's argument requires that the choice of measurement be free of the state of the particles. Fixed polarizers do not deliver that. The loophole even has a name, or rather two names, for two aspects of the same worry: the locality loophole and the freedom of choice loophole. There was a second problem, and this one had been spotted in 1970 by a physicist named Philip Pearl. Detectors are bad. They were very bad in 1972. Out of every batch of photon pairs the calcium produced, the experiment registered a tiny fraction. So the data being analyzed was not the data, it was a sample of the data, and the whole argument rested on an assumption that the sample was representative. Physicists call it the fair sampling assumption, and it sounds so reasonable that it is easy to miss what it costs. Here is what it costs. If the particles are allowed to carry instructions, there is nothing stopping the instructions from including one about whether to be detected. A pair that says, if you are asked at an awkward angle, do not trigger, the detector would bias the surviving sample in exactly the way needed to fake a violation. That sounds like an absurd conspiracy, and it is, but the whole point of Bell's theorem was that it ruled out absurd conspiracies without having to argue about how plausible they were. As soon as you have to say, yes, but that would be ridiculous, you have stopped proving and started persuading. The threshold matters. For a maximally entangled pair, you need to detect more than about 83% of them before the detection loophole closes on its own. Clauser and Friedman's photomultipliers were operating in the low single digits of percent. They were not close. Nobody was close. Nobody would be close for another 40 years. And then the experimental record did something that never appears in the tidy version of this story. It contradicted itself. Richard Holt, the fourth author of the CHSH paper, was building his own version at Harvard with Frank Pipkin. Instead of calcium, they used mercury. In 1973, they got a result, and their result agreed with local, hidden variables. It obeyed the inequality. It disagreed with quantum mechanics. They did not rush it into print. Holt and Pipkin were careful people, and the result was extraordinary enough that they went looking for what might be wrong with it before they went looking for a headline. For a period in the early and middle 1970s, the field simply had two experiments pointing in opposite directions, and the honest position of anybody watching was that nothing had been settled. The resolution, when it came, was not a philosophical argument. It was a piece of glass. The mercury vapor was contained in a bulb, and the bulb had been sealed in a way that left the glass under mechanical stress. Stressed glass is birefringent. It rotates the polarization of light passing through it by an amount that varies across the surface. That small, invisible, mechanical fact was quietly scrambling the very thing the experiment was trying to measure, washing out the correlation until the data looked classical. There is a general lesson buried in the mercury bulb that is worth taking out and holding up, because it applies to a great deal more than this. The contradictory result was not caused by bad physics or bad reasoning or a bad idea. It was caused by a manufacturing detail in a container. Somebody sealed a glass bulb slightly too tightly, and the resulting internal stress produced a systematic error that pointed a whole field in the wrong direction for several years. Almost every serious disagreement in experimental science looks like this from the inside. Not a clash of theories, but a slow, unglamorous hunt through the apparatus for the thing nobody thought to check. Clauser himself went back and rebuilt Holt's experiment in 1976, using a different isotope of mercury, and got the quantum result. In the same year, Edward Fry and Randall Thompson at Texas A&M ran a mercury version with one crucial improvement. Instead of a broadband lamp, they used a tuned laser to excite exactly the transition they wanted. The event rate went up by so many orders of magnitude that they collected decisive statistics in about 80 seconds of running time. 80 seconds. Against Berkeley's 200 hours, the violation held. So by the late 1970s, the picture was this. 3 experiments said the inequality was violated. 1 had said otherwise and had been traced to a flaw. The detection loophole was wide open, and there was no technology on the horizon that would close it. And the locality loophole, the one Bell himself had raised, was untouched, because in every experiment ever run, the polarizers had been sitting still. Closing that one required something that sounds, on first hearing, impossible. You have to decide what question to ask after the particles are already on their way, not a fraction of a second before they arrive. After they have left the source, while they are in flight, in a window measured in billionths of a second, because photons are not slow and a laboratory bench is not long. Somebody was about to work out how to do it, in a suburb south of Paris, and it was going to take him nearly 10 years. Alain Aspect read Bell's paper in 1974, and it did to him what it had done to Clauser. He decided to build the experiment that would close the loophole, and he decided to do it as his doctoral thesis. Before he started, he went to Geneva to talk to Bell in person. He explained what he wanted to do, and Bell's first question was not about the source, or the detectors, or the statistics. Bell asked him whether he had a permanent position. Think about what that question means. It is not small talk. It is not a courtesy. It is a warning, delivered by a man who had watched this field eat careers. To a young researcher about to walk into it, Bell was asking, "Can they fire you for this?" Aspect could answer, yes, he had one. He was already a slightly unusual case. He had spent 3 years teaching in Cameroon on national service, which had put him outside the normal French academic conveyor belt, and he had come back to a tenured post at the Institut d'Optique at Orsay, south of Paris. He was employed. They could not starve him out. He would need that, because the thesis took the better part of a decade. He began around 1974 and defended in 1983. There are universities today where a 9-year doctorate would be quietly terminated at year 4. He built 3 experiments, and each one closed something. The first, with Philippe Grangier and Gérard Roger, and published in 1981, used the same calcium cascade Berkeley had used, but excited it with lasers rather than an arc lamp. 2 lasers, tuned precisely, pumping the atoms up in a 2-step process that produced the cascade far more efficiently and with far less background. The coincidence rate went up by orders of magnitude. What had taken Clauser 200 hours now took minutes. The inequality was violated. The second, in 1982, went after a quieter weakness. Every previous experiment had used single-channel polarizers, a device that lets one polarization through and simply absorbs the other, which means that when a photon fails to arrive at the detector, you cannot tell whether it was blocked because it had the wrong polarization or whether it was lost for a boring reason. To interpret the data, you have to make an extra assumption about the missing photons. Aspect replaced them with two-channel polarizing cubes, which send both polarizations out along separate paths, each into its own detector. Now every photon that arrives gives an answer, plus or minus, and the extra assumption disappears. This is the first Bell test that corresponds directly to the experiment Bell described on paper. The result was S equals 2.697 plus or minus 0.015 against a local realistic ceiling of 2. That is a violation by roughly 46 standard deviations. In particle physics, 5 standard deviations is the threshold at which you are allowed to say you have discovered something. The third experiment is the one that made the Nobel, and it is the one that has to solve the impossible problem. To close Bell's locality loophole, you have to choose the measurement setting after the photons have left the source. That means changing a polarizer's orientation in less time than a photon takes to cross the apparatus. Photons cross laboratory benches in nanoseconds. Nothing mechanical moves that fast. You cannot spin a piece of glass in a billionth of a second. The glass would come apart, and long before it came apart, it would fail to keep up. Aspect's solution was to stop trying to move anything. He built what are called acousto-optical switches, and the principle is beautiful. Take a small cell filled with water, put electroacoustic transducers on it, driven at about 25 megahertz, and set up a standing sound wave inside the liquid. A sound wave is a pattern of compressions and rarefactions, which means a pattern of slightly different densities, which means a pattern of slightly different refractive indices. You have built a diffraction grating out of sound, and because it is a standing wave, that grating appears and disappears twice per cycle, roughly 50 million times a second. Light entering the cell now has 2 possible fates. When the grating is there, the light is deflected into one direction. When the grating is not there, the light goes straight through. 2 paths out of one cell, alternating tens of millions of times a second, with nothing physically moving except water molecules jiggling in place. Put a polarizer at one orientation on the first path and a polarizer at a different orientation on the second, and you have a device that changes which question it asks, without a single moving part. It is worth appreciating how much of this was plumbing rather than theory. To run the third experiment, the source had to sit at the exact geometric midpoint of a 12-meter optical path, and the alignment had to hold to a fraction of a millimeter, while a calcium oven ran hot at the center of it, and 2 water cells vibrated at 25 megahertz at either end. The building's own temperature drift over a night was enough to move things. Aspect has described the work in terms any experimentalist recognizes: years of getting a signal, losing it, and finding out that a cable had warmed up. The reason a doctorate took 9 years is not that the idea was hard to have. The idea took an afternoon. The apparatus took the decade. There is one more thing about the timing that deserves to be said. Aspect finished this in 1982. Bell was still alive, still at CERN, an hour's drive away. He saw it. Whatever else went wrong in this story, the man who wrote the theorem got to watch somebody close the hole he had found in his own result, and got to say so in print. He described Aspect's work as the most ideal Bell test then performed, and then, characteristically, went back to listing what was still open. Aspect ran 2 of these, one on each side, driven at deliberately mismatched frequencies so that their patterns never fell into step with one another. Now the numbers, because the numbers are the entire argument. The 2 detection stations sat about 12 to 13 meters apart, with the calcium source at the exact midpoint. Light needs about 40 nanoseconds to travel from one station to the other. The switches change state roughly every 10 nanoseconds. So in the time it would take any signal, traveling at the absolute speed limit of the universe, to get from one side of the experiment to the other, each switch had already changed its mind 4 times. Notice what that arrangement buys you, because it is easy to let it slide past. It is not merely that the setting is chosen quickly. It is that the 2 choices and the 2 outcomes are placed outside each other's light cones. Whatever happened at the left-hand station is, in the strictest relativistic sense, unable to be a cause of what happened at the right-hand station, and vice versa, because no influence of any kind travels faster than light. The experiment does not ask you to believe that no signal was sent. It arranges the geometry of space-time so that no signal could have been sent. That is why this experiment matters more than the raw statistics suggest. It converts a philosophical assurance into a fact about the shape of the room. Follow a single photon through it. It is born inside a calcium atom at the center of a darkened hall. At the instant of its birth, the question it is going to be asked does not exist. Nothing in the universe has decided it yet. The photon travels 6 meters, which takes it 20 nanoseconds, and in that time, the water cell ahead of it has flickered twice. It enters the cell, the grating happens to be there, or happens not to be, and the photon is sent along one of 2 paths, into one of 2 polarizers, and asked one of 2 questions. And its partner, 6 meters in the other direction, is asked a question chosen by a completely separate device running at a different frequency, at a moment when no news of the first photon's fate could possibly have reached it. The experiment was published on the 20th of December, 1982, in Physical Review Letters with Jean Dalibard and Gerard Roger. The inequality was violated by about 5 standard deviations, in agreement with quantum mechanics. Aspect himself was careful about what he had and had not done, which is the pattern in this story. The switching was fast, but it was not truly random. The standing waves were periodic, and a sufficiently determined conspiracy theory could point at that. It would take another 16 years to fix. In 1998, Gregor Ways, working with Zeilinger in Innsbruck, ran the same test with genuine physical random number generators, making the choices, and with the 2 stations 400 meters apart on a university campus rather than 12 meters apart on a bench. The violation came in at 30 standard deviations. So by the end of the 1980s, the position was this. The locality loophole was effectively shut. The detection loophole was wide open and looked unshuttable. And the field had a phenomenon it could now produce reliably, characterize precisely, and not explain at all. Which raises a question that turns out to be the hinge of this entire story. What do you do with something you cannot explain, but can control? Before we go any further, let us stop and stack up what we actually have, because we are about halfway through, and the ground has shifted several times. We started with 2 boxes, and a very reasonable belief, that things have properties, whether or not anyone is looking, and that what you do here cannot instantly change what happens there. Realism and locality. Together, local realism, and it is the assumption underneath essentially every explanation science produced between Newton and the 1920s. Einstein, in 1935, showed that quantum mechanics is incompatible with that belief unless the theory is incomplete, and concluded that the theory must be incomplete. Bohr disagreed. The field agreed with Bohr for reasons that had more to do with success than with argument, and the question was closed without being answered for 30 years. Then Bell, in 1964, showed that the question was not philosophy after all. Any locally real world, of any construction whatsoever, must keep a certain measured number below 2. Quantum mechanics says the number goes above 2. Somebody just had to count. Clauser and Friedman counted, at Berkeley, in 1972, and the number went above 2. Bell then pointed out that their polarizers had never moved, which left a way out. Aspect, at Orsay, in 1982, changed the question while the photons were already in flight, and the number still went above 2. What remains open at this point in the story is one thing, and it is a real thing, not a technicality. The detectors were still catching only a small percentage of the particles, and the whole result rested on assuming that what they caught was representative of what they missed. Nobody in 1982 could see how to fix that. So here is the strange turn the field takes next. Instead of waiting, it changes the subject. For about 30 years, from the mid-80s onward, the most interesting work on entanglement is not about testing it, it is about using it. And the reason the Nobel Prize arrived in 2022 rather than 1985 is sitting inside that sentence. Though we are not going to unpack it fully, until the end. The person at the center of the turn is the third laureate. Anton Zeilinger was born in Austria in 1945 and built his career in Vienna and Innsbruck. He came into this field from neutron interferometry rather than from the Bell test tradition, and he brought with him a habit of asking not just whether entanglement was real, but what could be done with it if you got good enough at making it. In December of 1997, his group in Innsbruck published a paper in Nature reporting the first experimental demonstration of quantum teleportation. The authors were Dick Baumeister, Jianwei Pan, Klaus Mattel, Manfred Eibel, Harold Weinfurter, and Zeilinger. The protocol had been worked out on paper 4 years earlier by Charles Bennett and 5 colleagues, and it is worth understanding because it is the single clearest demonstration that entanglement is a resource rather than a curiosity. You have a particle in some unknown quantum state, and you want that exact state to appear on a particle somewhere else. You cannot measure the original and send the numbers, because measuring destroys the superposition and gives you one answer where the state contained many. You cannot copy the original either. The no-cloning theorem forbids making a duplicate of an unknown quantum state, and that is a hard theorem, not an engineering limitation. What you can do is this. Ahead of time, distribute an entangled pair, one member to each end. Then, at the sending end, perform a joint measurement on your unknown particle together with your half of the entangled pair. That measurement scrambles both of them and gives you a result which, on its own, is meaningless. 2 bits of apparently random information. Send those 2 bits to the far end by ordinary means. A phone call, an email, anything, at any speed up to but not exceeding light. At the far end, those 2 bits tell the receiver which of 4 simple operations to perform on their half of the entangled pair. They perform it. And their particle is now in precisely the state your particle was in. Notice several things at once. Nothing material has travelled. The state has moved. The substance has not. The original state is gone, necessarily, destroyed by the joint measurement. So this is a transfer rather than a copy, which is exactly what no cloning requires. And crucially, until those 2 classical bits arrive, the receiving end has nothing at all. Their particle is in a random state, and no measurement they can perform will reveal anything. The entanglement does half the work instantly, and the half that carries meaning crawls along at the speed of everything else. That last point is the reason quantum teleportation is not, and can never be, a faster-than-light communication system. People assume the opposite so consistently that it is worth saying twice. The instantaneous part carries nothing you can read. The readable part is a normal message obeying normal limits. A year later, in 1998, Pan, Baumeister, Weinfurter, and Zeilinger did something that I find harder to hold in my head than teleportation. It is called entanglement swapping. Take 2 entangled pairs, made separately, in different places. Call them A with B and C with D. A and B know about each other. C and D know about each other. A and D have no relationship whatsoever. They have never interacted, never been in the same place, and have no shared history at all. Now bring B and C together and perform a joint measurement on them of the same type used in teleportation. That measurement destroys B and C as independent things. And when it is done, A and D, which have never met, are entangled with each other. Later versions of this experiment pushed it somewhere stranger still. In 2012, Zeilinger's group ran a delayed choice version in which the decision to entangle 2 photons was made after both of them had already been detected and destroyed. The 2 photons that end up entangled never coexist. There is no moment in the history of the universe at which both of them are present. There is a way of picturing swapping that helps, though like all pictures of this, it eventually breaks. Think of entanglement not as a link between 2 particles, but as a single relationship with 2 ends. Teleportation moves one end of a relationship onto a new particle. Swapping takes 2 separate relationships and splices them at the middle, so that the 2 loose ends, which never had anything to do with each other, become the 2 ends of one relationship. Nothing travels along the splice. There is no wire. The measurement in the middle is not sending anything anywhere. It is changing what kind of relationship exists. and the change is not located in any particular place. If that last sentence feels slippery, good, it is meant to. The vocabulary of things and places, which has served physics faithfully since Newton, is beginning to creak here, and by the end of tonight, we are going to look directly at the possibility that the vocabulary is what is wrong. Entanglement swapping is not a party trick. It is the operating principle of a quantum repeater, and a quantum repeater is the only known way to build a quantum network longer than a single unbroken run of fiber, because entanglement degrades over distance, and you cannot amplify it the way you amplify a classical signal. Every serious proposal for a quantum internet is built on this. The same group also produced the first three-particle entangled states, called GHZ states, after Daniel Greenberger, Michael Horn, and Zeilinger, who proposed them in 1989. Those states do something Bell's two-particle version cannot. With two particles, local realism predicts a smaller average correlation, and you need statistics to see the difference. With three, local realism does not predict a smaller average. It predicts the opposite outcome with certainty every single time. A GHZ test is Bell's theorem without an inequality, one measurement, and the local realist is not slightly off. They are exactly wrong. There is a footnote to the GHZ story that belongs to the theme of this evening. Two of the three people whose initials are on those states, Daniel Greenberger and Michael Horn, are not on the Nobel citation. Horn, who was also the H in the middle of CHSH, died in 2019, 3 years before the prize. Greenberger was alive and 90 in 2022, and the statutes cap the award at 3 people. And once you can make entangled states on demand, swap them, transfer states between them, and verify them, you no longer have a philosophical puzzle. You have a component. On the 21st of April, 2004, a small amount of money moved from an account at Vienna City Hall to an account at a branch of Bank Austria Kreditanstalt. It was an ordinary bank transfer in every respect except one. The key that encrypted it had been generated using entangled photons, sent through about 1.5 kilometers of optical fiber running through a sewer duct beneath the city. It was the first bank transfer in history secured by quantum key distribution using entanglement, and Zeilinger's group did it partly to make a point. The point was that the argument Einstein and Bohr had been having was no longer confined to seminar rooms. It was underneath the street, doing a job. The reason quantum cryptography matters is not that it is stronger encryption, it is that it is a different kind of security altogether. Every conventional encryption system in use today rests on the assumption that a particular mathematical problem is hard, that factoring an enormous number, or something like it, would take a computer longer than anyone is willing to wait. That is an assumption about capability, and capabilities improve. Everything encrypted this way is, in principle, breakable by someone with enough time or a sufficiently clever algorithm, and a large enough quantum computer is precisely the machine that would make several of those problems easy. Quantum key distribution does not rest on difficulty. It rests on the fact that measuring a quantum system disturbs it. An eavesdropper who intercepts the photons carrying the key has to measure them to learn anything, and measuring them changes them, and the change shows up at the far end as an error rate in the key. The two legitimate parties compare a sample of their key openly, see the error rate, and know they have been listened to. You cannot listen quietly. The physics does not offer that option. Behind that guarantee sits a theorem with a memorable name, the monogamy of entanglement. If two particles are maximally entangled with each other, then neither of them can be entangled with anything else at all, not a little bit, not weakly, not at all. An eavesdropper cannot quietly become a third party to a maximally entangled pair, because the mathematics has no room for a third party. Bell's abstract argument about instruction sets, 60 years on, has turned into the reason a channel cannot be tapped. It is worth being honest about the limits here as well, because quantum cryptography attracts more excitement than it can carry. It secures the distribution of a key. It does not secure the room the key is used in, the operating system it is stored on, or the person who writes it on a whiteboard. It does not make a network unhackable. It removes one specific category of attack, the quiet interception of key material, and leaves every other category exactly where it was. The engineering is also unforgiving. Photons are absorbed by glass, so the practical range through fiber without repeaters is a few hundred kilometers at best, and every kilometer costs you signal. This is a real technology with real limits, not a magic envelope, and the channel that tells you otherwise is selling something. The distances then started to grow. In 2007, Zeilinger's group distributed entangled photons across 144 kilometers of open air between telescopes on La Palma and Tenerife in the Canary Islands, using the same optical ground station the European Space Agency used for satellite laser links. In 2012, they used that same link to teleport quantum states across the same distance. There is a lovely, slightly absurd detail about the ground station work that says something about how experimental physics actually gets done. The Canary Islands link was chosen because the atmosphere above the Atlantic between La Palma and Tenerife is unusually stable, and there was a telescope at each end already pointing the right way, which means that one of the more important demonstrations in the history of quantum information was arranged in part around the availability of two mountain observatories and the weather. Then it went up. On the 16th of August, 2016, China launched a satellite called Mikius, a 631-kilogram spacecraft in a 500-kilometer sun-synchronous orbit. It was named after Mozi, a Chinese philosopher of the 5th century before the Common Era, who, among other things, left the earliest written description we have of a camera obscura and of light traveling in straight lines. It is a good name for a satellite whose job is to shine entangled light at the ground. In 2017, a team led by Pan Jianwei used Mikius to distribute entangled photon pairs to two ground stations 1,203 kilometers apart and demonstrated that the correlations survived. The result was published in Science. The reason a satellite works when fiber does not is that atmospheric loss is concentrated in the lowest 10 kilometers or so of the path. Above that, the beam travels through near vacuum. The link efficiency was something like 1 trillion times better than the same distance would have given in glass. In 2018, the same infrastructure carried an encrypted video call between Beijing and Vienna with the key material distributed by satellite. Pan Jianwei, who built that program, did his doctorate in Innsbruck under Anton Zeilinger and was a co-author on the 1997 teleportation paper. The line of descent runs directly from a laboratory bench in Austria to a national quantum communications program. Meanwhile, entanglement had become the working substance of an entirely different technology. A quantum computer is not fast because it tries every answer at once, whatever you have read. It is capable of things. A classical computer is not, because it can build and manipulate entangled states across many qubits, and interference between those states can be arranged to cancel wrong answers and reinforce right ones. Strip out the entanglement, and a quantum processor is an expensive and rather bad classical computer. Every entangling gate in every machine being built today is a controlled, deliberate act of the thing Einstein called spooky. Zeilinger's group did a great deal of other work in the same years that is worth knowing about, because it shows the same instinct applied in a different direction. Working with Marcus Arndt in 1999, they sent buckyballs through a double slit and got an interference pattern. A buckyball is a molecule of 60 carbon atoms, a football of graphite, an object with a temperature and an internal structure and vibrational modes, and it behaved like a wave. Later, experiments in the same program pushed that to molecules of more than 2,000 atoms. The point of those experiments is not entanglement, but the attitude is identical. Take the thing everybody agrees is only true for tiny abstract particles, and keep making the particle bigger until somebody has to explain where the boundary is. Nobody has found the boundary. There is one more application that deserves a mention, because it is the strangest example of a philosophy paper turning into a product. It is called device-independent randomness generation. Suppose you need random numbers that nobody, including the manufacturer of your equipment, could have predicted or pre-recorded. Ordinary hardware cannot give you that, because you have to trust the hardware. But if you run a Bell test with your 2 boxes and the number comes out above 2, then the outcomes cannot have been pre-written. That is precisely what a Bell violation means. The randomness is certified not by trusting the device, but by the violation itself. In 2022, groups in Oxford, Munich, and Geneva demonstrated complete device-independent key distribution built on this idea. So this is the answer to the question we ended the last part with. What do you do with something you cannot explain but can control? You sell it. Or rather, a phenomenon that started as an argument about whether a question was even meaningful became, over about 30 years, a set of components with datasheets. By 2022, there were commercial quantum key distribution networks in service. A 4,600-kilometer quantum communications backbone running between Beijing and Shanghai, and error-corrected quantum processors whose entire operating principle is the deliberate manufacture and preservation of entangled states. And that, though we are still not ready to say it plainly, is a large part of why the Nobel Prize came in 2022 rather than in 1985. But while the engineers were building, the experimentalists had not stopped. There was still one loophole open. It had been open for 43 years. And, in a single autumn, 3 different groups on 2 continents closed it. Let us be precise about what was still open in the year 2000, because this is where the story gets its ending. There were 2 ways out, and no experiment had ever shut both at once. The first is the locality loophole. If the 2 ends of the experiment can communicate at or below the speed of light during the measurement, the result proves nothing. Aspect closed this in 1982 by switching in flight, and Waze closed it properly in 1998 with genuine random choices and 400 meters of separation. The second is the detection loophole. If your detectors only register a small fraction of the particles, a local model can hide inside the missing majority. To close it, you need to detect most of the pairs you produce, and the threshold for a maximally entangled pair is about 83%. For decades, no photon detector came close. There was a technology that could close the detection loophole. In 2001, David Wineland's group at the American National Institute of Standards and Technology in Boulder ran a Bell test on 2 beryllium ions held in an electromagnetic trap. Trapped ions can be read out with essentially perfect efficiency. You shine a laser on them, and they either fluoresce or they do not, and you see it every time. The inequality was violated with no fair sampling assumption at all. But the 2 ions were about 3 micrometers apart, which is a few hundredths of the width of a human hair. Every part of that experiment was inside every other part's light cone by an enormous margin. The detection loophole was shut, and the locality loophole was open as wide as a door can be. So the field had 2 kinds of experiment that each closed the loophole that the other left open, and for 15 years that was the state of play, and it was a genuinely uncomfortable state of play, because a sufficiently determined critic could always say, "You have never done both at once, and a local model only has to survive in one of them." The idea that broke the deadlock came from a theorist named Philippe Eberhard in 1993. Eberhard noticed something counterintuitive. If you use a pair that is not maximally entangled, but only partly entangled, the violation you can achieve is smaller, but the detection efficiency you need to prove it drops sharply from about 83% to about 67%. That is still very demanding, but it is on the edge of possible, and it moved the target from unreachable to merely extremely hard. Almost every loophole-free experiment run since is built on Eberhard's observation, and he made it more than 20 years before anybody could use it. The equipment caught up in the 2010s in the form of superconducting transition-edge sensors, detectors cooled to a fraction of a degree above absolute zero, sitting exactly at the point where a material stops superconducting, so that the energy of a single arriving photon is enough to tip them. Efficiencies above 90% became possible. And then, in a single autumn, it was over. In October 2015, a group led by Bas Henson at Delft published in Nature. Their approach was different from everyone else's. Instead of photons, they used the spins of single electrons trapped at nitrogen vacancy centers in diamond, which are essentially single atoms of nitrogen sitting in a carbon lattice next to a gap. One diamond sat in a laboratory on the Delft campus. The other sat 1.3 kilometers away. Electron spins can be read out with essentially perfect efficiency, which kills the detection loophole, and 1.3 kilometers gives you more than 4 microseconds of light travel time, which kills the locality loophole. To entangle two electrons that far apart, they used entanglement swapping. Each diamond emitted a photon, entangled with its own electron. Both photons traveled to a third station in the middle, and a joint measurement there entangled the two electrons that had never met. It worked, and it worked at an agonizing rate. They ran the experiment for 220 hours across 18 days and collected 245 usable trials. That is one event roughly every 90 minutes. On that handful of data, the measured value of S came out at 2.42, plus or minus 0.20, against a ceiling of 2, with a probability of about 4% that local realism could have produced it by chance. It is worth pausing on how thin that dataset is, because it cuts against the way we usually imagine a decisive experiment. 245 events is fewer data points than a small clinical trial. It is fewer than the number of people in a school assembly. The single most consequential experiment in the foundations of physics, the one that finally shut a door that had stood open since 1935, rests on a sample you could write out longhand on a few sheets of paper. That is what it costs to insist on doing something properly rather than nearly. And there were the ordinary indignities that never make the abstract. Delft ran across a Dutch campus in winter, through a fiber link that had to be phase stabilized over more than a kilometer while the ground temperature changed under it. Every failed attempt, and there were tens of millions of them, had to be logged and accounted for in advance, because deciding after the fact which runs counted would have opened a loophole of its own. 4% is not overwhelming, and everybody knew it, which is why the two experiments that followed within 8 weeks mattered so much. In December 2015, Marissa Justina and colleagues in Vienna, and Lyndon Shalm and colleagues at Boulder, published photon experiments in the same issue of Physical Review Letters, both loophole-free, both using the new detectors, both with far more data. The Boulder result corresponded to a probability of roughly 1 in 10 billion that a local, realistic world could have produced it. 3 groups, 2 continents, 3 different physical systems, diamond electron spins, and photons twice over, 3 months. And after 80 years of argument and 43 years of experiment, the last honest way out was gone. Except for one, and it is the one Bell had always known was there. Where do the measurement settings come from? The theorem assumes the choice of question is free of the state of the particles. What if it is not? 2 experiments went after that with a kind of glorious literalism. On the 30th of November, 2016, 13 laboratories on 5 continents ran Bell tests simultaneously, and the settings were chosen by human beings. About 100,000 people around the world played a simple online game designed to extract unpredictable choices out of them, generating roughly 97 million bits, which were streamed live to the laboratories to set the polarizers. It is called the Big Bell test, and it was published in Nature in 2018. If the settings had been chosen by a machine, you could argue about the machine. Instead, the settings were chosen by 100,000 people tapping their phone screens, and for the conspiracy to work, every one of those taps had to have been coordinated with the particles. And then somebody went further and used the sky. In 2017, Johannes Hansteiner and colleagues, working with Zeilinger, used the color of light arriving from stars, about 600 light-years away, to set the polarizer angles. In 2018, Dominic Rauch and colleagues repeated it using 2 quasars, one whose light had been traveling for about 7.8 billion years and one at about 12.2 billion. Sit with that for a moment. A photon leaves a quasar 12 billion years ago. The Earth does not exist. The Sun does not exist. The atoms that will one day be in your body are still inside stars that have not yet finished making them. That photon crosses expanding space for 12 billion years, and it arrives at a telescope on a mountain in the Canary Islands. and its color, decided in a distant galaxy in the early universe, determines the angle of a piece of glass for a few billionths of a second. Down on the bench, a pair of entangled photons is asked a question whose answer was fixed in a galaxy that no longer exists, and the correlations still break the ceiling. For a local hidden variable conspiracy to survive that experiment, the conspiracy would have had to be arranged before the solar system condensed out of dust. Which brings us back to the number, a number that cannot go above 2. That was Bell's ceiling, and it was not a prediction about quantum mechanics. It was a hard arithmetic limit on any world made of things that carry their properties and mind their own business. In Delft, in 2015, with every loophole shut, that number came in at 2.42. It went above 2, and then it stopped, because quantum mechanics has a ceiling of its own. The maximum possible violation at the very best angles with the very best states is 2 times the square root of 2, about 2.828. It is called the Tsirelson bound, after Boris Tsirelson, who proved it in 1980. Nature never exceeds it. Here is the part nobody has explained. There is no logical reason for the ceiling to be there. In 1994, Sandu Popescu and Daniel Rawlik showed that you can write down perfectly consistent correlations, far stronger than quantum mechanics allows, which still cannot be used to send a message and still break no law of relativity. Those hypothetical correlations go all the way up to 4. Nothing forbids them except the fact that we do not find them. So the universe is stranger than common sense allows, and tamer than logic permits, and it stops at a very specific number for no reason anyone can give. That is still open. It may be the most important open question in the whole subject. One more thing before we go to the last part, and it is not a happy one. John Bell never saw any of this. He wrote the theorem in 1964, in a borrowed year, on a topic he called a hobby, published it in a journal that folded, waited 5 years for a single letter, and then spent the next quarter of a century patiently pointing out the flaws in every experiment that confirmed him, while hoping in public that one of them would prove him wrong. On the 1st of October, 1990, he died of a cerebral hemorrhage in Geneva. He was 62. He had been nominated for the Nobel Prize that year. He died 25 years before the experiments that finally closed the loopholes he himself had identified, and 32 years before the prize that his 4 pages made possible. So, it is settled, which leaves only the question of what, exactly, was settled. And this is where physics stops agreeing with itself. Here is the sentence that has been sitting under this whole evening, and it is worth reading slowly, because everything now depends on the small word in the middle. The world is not both local and real. That is what the experiments established. Not that the world is non-local, not that things have no properties, that the two together cannot both be true. Bell's theorem is a statement about a conjunction, and the experiments killed the conjunction, and basic logic tells you that when a conjunction is false, at least one of its parts is false. It does not tell you which. 50 years of increasingly beautiful experiments have narrowed every escape route, and none of them has told us which word to bury. That is the strangest thing about this result, and it is the thing that survives least often into a headline. The universe has refused, in the most emphatic and reproducible way available to it, to be locally real, and it will not say which half it minds. So physics has to choose. And there are exactly 4 ways to choose, and every one of them costs you something you would rather keep. The first choice is to give up realism. You say that the properties genuinely do not exist until a measurement occurs, that asking what the photon's polarization was before you measured it is not a question about the world at all. This is roughly the orthodox position, the one that grew out of Copenhagen. Its cost is that it depends completely on a word it cannot define. What is a measurement? Nothing in the Schrödinger equation singles out measurements as special events. The equation describes smooth, deterministic evolution, and it applies to atoms, to detectors, to laboratories, and to physicists. Nowhere in the mathematics is there a line marked, here is where possibilities become facts. Nobody has ever found that line experimentally, and every attempt to push it further away has failed to find a wall. You can have a world where properties come into being at measurement, but you cannot yet say what event you are talking about. The second choice is to give up locality, keep the properties. Say the ball really was white in the box, and accept that when you opened your box, something changed on the moon. This is not a joke position, it is a fully worked out theory. Bohm's pilot wave, the one written in exile in Sao Paulo, does exactly this and reproduces every prediction of standard quantum mechanics, exactly, with no exceptions. Particles have definite positions at all times, guided by a wave. The cost is written into the guiding equation. The motion of a particle here depends, instantaneously, on the configuration of particles arbitrarily far away. And to define instantaneously, you need a universal present moment, a preferred slicing of time that everybody shares, which is precisely the thing relativity says does not exist. Bohmian mechanics is arranged so that this non-locality can never be used to send a signal, so it never contradicts relativity in practice. But it sits badly, in the way a lodger sits badly in a house where they are technically allowed to live. The third choice is to give up single outcomes. In Everett's formulation, better known as many worlds, nothing ever collapses. The measurement on your side produces both results, the measurement on the far side produces both results, and the branches only sort themselves out when the two records are brought together and compared. There is a technical sense in which this is a perfectly local theory. Nothing has to be decided at a distance because nothing is decided anywhere. Its cost is the ontology, which is an enormous, permanently unobservable, endlessly branching structure containing every version of everything, and a long-running difficulty in explaining why probabilities come out the way they do when, in a certain sense, everything happens. The fourth choice is the one people find hardest to take seriously, and the one that is logically the most watertight. Give up free choice. Remember that Bell's theorem assumes the measurement settings are independent of the state of the particles. If that independence fails, the theorem does not apply and nothing has been proved at all. This is called superdeterminism, and it has been defended by serious people, including the Nobel laureate Gerard 't Hooft and the physicist Sabine Hossenfelder. The idea is that the particles and the random number generator and the human tapping a phone screen and the quasar whose light chose the polarizer angle all share a common determination reaching back to the initial conditions of the universe, and that the correlation between them was set at the beginning. You cannot experimentally refute that. Nobody can. The quasar test makes it more extravagant because the conspiracy has to be older than the solar system, but extravagance is not refutation. Bell himself acknowledged that the logic was airtight and said he did not believe a word of it, and the standard objection is not that it is impossible, but that it is corrosive. If the settings of an experiment can be correlated with the system under study, then no controlled experiment anywhere in science is trustworthy, including the ones that would establish superdeterminism. It saves locality and realism by making the practice of science incoherent. There is a fifth option, quieter than the others, which is to allow influences to run backwards in time within light cones. Retrocausal and time-symmetric formulations preserve locality in space at the price of temporal order, and no experiment currently distinguishes them from the alternatives. Take a moment with that list. Properties do not exist until you look, or distance is not real separation, or every outcome happens, or you could not have chosen otherwise, or the future reaches back. One of those is true, not one of them is a small adjustment. Every single one of them takes away something so basic that most people have never noticed holding it. Now, let us go back to the boxes, because there is one thing left to settle there. Nothing travelled, you only learned. That was the comfortable verdict on the classical version, and here is the thing, it is still true. It is a theorem, in fact, with a name. The no communication theorem says that nothing your partner does to their half of an entangled pair changes anything you can observe about yours. Your outcomes are random. They are random if your partner measures. They are random if your partner does not measure. They are random whatever angle your partner chooses and whatever they find. There is no experiment you can perform on your particle that reveals whether the far end has been touched at all. The The correlation only appears when the two records are laid side by side, and laying them side by side requires an ordinary message, traveling at ordinary speed. So nothing was sent. Nothing can be sent. Entanglement is not a faster-than-light telephone, and it never will be one, and every scheme claiming otherwise turns out on inspection to have smuggled in a classical channel or assumed you can copy an unknown quantum state which is forbidden. If you have read that quantum entanglement will one day let us talk instantly across the galaxy, that is the one thing we can say with total confidence it will not do. And while we are clearing the ground, entanglement is also not a link between people or minds or intentions. It is a fragile relationship between quantum degrees of freedom, and it is destroyed almost instantly by contact with anything warm and noisy, which includes air, light, and the inside of a human body. The extraordinary difficulty of building a quantum computer, of keeping a handful of particles entangled for a fraction of a second at temperatures near absolute zero behind layers of shielding, is the same physics that rules out entangled people. That is not a dismissal of anybody's beliefs. It is just what the word means in the place it came from. So, nothing travelled, and you only learned, and the sentence has kept every word and lost all its comfort. Because in the classical story, that sentence was true, because the answers were already there. In the real world, no signal passed, and the answers were not already there. And both of those things are true at once, and nobody knows how to draw the picture. There is one direction the field has started to look, and I want to flag clearly that this is speculation at the frontier rather than established physics. It is the suggestion that the question, how does the influence get across the distance, may be the wrong question, because distance itself may be built out of entanglement rather than being the stage it plays on. In 2006, Shinsei Ryu and Tadashi Takayanagi found a formula relating the entanglement in a quantum system to the area of a surface in a higher dimensional spacetime. In 2010, Mark van Ramsdonk showed that if you take such a system and steadily remove the entanglement between two halves of it, the corresponding geometry pulls apart, and at zero entanglement, the two regions are no longer connected at all. Space comes apart when you remove the entanglement. In 2013, Juan Maldacena and Leonard Susskind proposed that an entangled pair and a microscopic wormhole might be the same object, described two ways. If any of that is right, then entangled particles are not two things reaching across a gap. They are the reason there is a gap. And asking what crosses, it is like asking what color a number is. So, finally, the real reason. Read the citation one more time, and this time, read all three clauses for experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. The prize was not given because three men proved entanglement is real. It was not given because they proved Einstein wrong, and Einstein was not wrong about anything he actually claimed. He claimed the theory was incomplete, and what the experiments showed is that the specific kind of completion he wanted is impossible. The prize was given because, over 50 years, one careful experiment at a time, these three men and the people around them closed off every remaining way in which the universe could have been locally real. Berkeley took away the option that the correlations were not there. Orsay took away the option that the two ends were talking to each other. Delft and Vienna and Boulder took away the option that the detectors were lying. 100,000 strangers on their phones and the light of a quasar older than the Earth took away the option that the choices were rigged. What is left is a hole in the floor of physics that has now been measured to a confidence of 1 part in 10 billion and that nobody can fill. And they did it while turning the anomaly into an industry. That is the third clause, and it is the reason the prize arrived in 2022 instead of 1985. The Nobel Committee does not usually reward foundations. It rewards foundations that grew a technology, and the technology took 30 years to arrive. There is a fourth reason, unofficial, that a good many physicists believe, and that the committee would never write down. The prize was an apology. For 3 decades this question was called philosophy, and the people who insisted on asking it were told they were wasting equipment and damaging their prospects. And one of them was thrown out of Richard Feynman's office, and told the thing needed no further testing. It needed no further testing. Hold that sentence up now, at the end, and look at what came out of testing it, anyway. Quantum key distribution, quantum repeaters, certified randomness that no adversary can have pre-recorded, teleportation of quantum states between islands and between continents, satellite links, the entangling gates inside every quantum processor being built on Earth. All of it descended, directly and traceably, from a handful of people who refused to accept that a question was closed, working on a phenomenon that the most admired physicist of the age had told them was not worth the bench space. And now, the part that is not about laboratories. You are lying somewhere, and around you there are things, the bed, the floor under it, the walls, your own hands. Every one of those is made of the same stuff as the photons in a calcium cascade in a basement in Berkeley, obeying the same rules, and the experiment has been run, and the answer has come back, and it is this. At least one of the two things you have never once questioned about, all of it is false. Either those things do not have their properties while nobody is looking at them, or what happens to them here is not independent of what happens somewhere else. There is no third option that anybody has been able to find in 90 years of trying. That is not a frightening thought, I do not think. It is a settling one, in its way. The world you are lying in is not the sturdy assembly of separate objects that common sense reports. It is something more intricate and less divided, in which separation is not quite what it appears to be, and in which a photon and its partner, born together and dragged 1,200 kilometers apart, still behave as though the word apart were a rough approximation rather than a fact. And the last thread, the one nobody has pulled, the ceiling, 2.828. That is as far as nature will go, not 2, which common sense allows, not 4, which logic permits. Somewhere in between, at a number that falls out of the mathematics and has never been derived from anything deeper. Whatever the correct account of all this turns out to be, it will have to explain not only why the universe is stranger than Einstein could accept, but also why it is not as strange as it is allowed to be. Thank you for spending this time with me, following one very stubborn question from a 4-page paper in 1935 to a satellite in orbit. If this is the kind of exploration you like to fall asleep to, a like or a subscribe would mean a great deal. It genuinely helps me keep making these. And remember, the next time you notice two things sitting quietly across a room from each other, that the space between them may be doing less work than you think. Good night, and may you never look at the word apart the same way again.